Get started then. Sri, thank you very much for coming here.
Oh, you're welcome. Yeah.
So it's my pleasure to introduce Sri, and he is the vice president of technology at Halliburton.
Mm-hmm.
He is a PhD in aerospace engineering from University of Virginia.
Yep.
Right. He's worked at United Technologies and also at Pratt & Whitney.
Mm-hmm.
And he has been really instrumental in this new technology that we're going to discuss today, which is innovation in really a new, almost fully autonomous or autonomous-enabled drill bit, which is used in fracking and many of the other oil field services that Halliburton provides. So we just to level set the conversation. We're primarily going to talk about this new technology. I've drafted a case with Sri's help over the last few months about the technology, and I'm assuming all of you have read that. We'll briefly talk about what's in the just to get everyone on the same page, and then we'll go into more details about how this technology emerged, what challenges and problems Halliburton faced in developing it, what are the barriers to some of that innovation, how they overcame those obstacles, and how the technology is doing. Does that sound good?
Yep.
Okay, great.
Perfect. So, I don't know how much if you know about oil field services or oil and gas in general. Should I assume that you know a lot, or no?
It's a mix.
It's a mix. So maybe a little sort of, just to get everybody on the same page. So, if you look at, the life cycle of a well, generally, the big players in this industry, in the upstream industry, are oil companies like Shells and Aramcos and BPs, as well as the small operators in the U.S. land in the shales. Then you have oil field services companies such as Halliburton, Schlumberger, Baker Hughes, and so on. And so, the oil companies own the assets, the real estate and the mineral rights. And so they contract the oil field services companies to perform services for them in order to extract this oil and gas. And so then, the life of the well begins generally, if you have a field where you have a discovery, where, for example, if you look at U.S. land right now, the hottest area is the Permian Basin in Texas. And so, there's this first phase where the life of the well begins. It's the exploration. So you have a huge field. You have to explore it and find where the oil and gas is, subsurface. And then the problem can be summarized as 4 questions. Where to drill, how to drill, where to frack, and how to frack. And so that's sort of the essence of what, the questions that oil companies want answered, and what the oil field service companies like Halliburton deliver solutions to answer those questions. So coming back to the life of the well, you see, you drill the well, it's called open hole drilling, just like bare rock. You go in with a drilling, system, and such as what's shown here, and literally it drills the well. And, huge technological advancements have been made over the last 15 years, especially driven by the shale revolution in the U.S., and which has allowed us, the industry, to dramatically reduce drilling time. So, we drill today at the rate of, as high as 500 feet an hour, which is like remarkable, to drill at those rates. So which means that within a week you can drill a well which is like 5 miles long. And so you see horizontal drilling, which is what this technology has enabled the industry, especially the shale, to sort of drill like factory drilling. I mean, this is what you see in all the shale plays in the U.S. And so drill, and then you complete a well. So which means you cement the well, and there's a casing, and then you cement it, and then maybe put some completions. Then comes the fracturing, the perforation and fracturing. So you have to like perforate the wells wherever you want the oil and gas to come into the well, and then you do hydraulic fracturing, which is, you pump water and sand, or water, chemicals, and sand into the well, literally to crack open the formation. The unique feature of a shale formation versus a conventional formation is that in a conventional formation, the oil reservoir literally is like oil sloshing around in a reservoir underneath, so it's easy for it to flow out, whereas in a shale, oil and gas is locked in place, and it cannot naturally flow unless you literally break open the formation. Hence, hydraulic fracturing. So you use water or fluids to break open the formation, and the sand, or proppant, which is pumped along with the water to hold open those cracks, allowing this hydrocarbons to flow back into the well and then up, and then you collect. So that's, and then the oil produces over the life of the well. At some point, you run out of oil from that well, and you have to abandon the well, and thus the well ends its life. So that's sort of the life cycle of the well. And Halliburton, as well as its competitors in the service space, offer the full spectrum of services across this life cycle. So, we're involved in drilling, in cementing, in perforating, in fracturing, and then producing, and then abandoning. So, and so in each of these sort of services, over the last 15, 20 years, has been huge advancements in technology, but especially so in drilling. And this sort of leads us to this particular thing that we'll talk about. And so some more sort of background in Halliburton-specific background, and this is all public knowledge, and why it's germane to this particular case. A few years back, and I think it was 2014 or so, especially when we had this huge downturn in the industry, Halliburton made an attempt to acquire Baker Hughes, right? Like big news. The number 2 and number 3 companies trying to come together for various reasons. So when that was happening, the idea at Halliburton was to divest our drilling business in favor of Baker's drilling business, because it was widely regarded that Baker's business products and that drilling business was superior to Halliburton's. Again, there are many reasons of why Halliburton's drilling business sort of came into a state of relative disrepair, right? I mean, it's a whole another discussion. But that was the situation in 2014 when this acquisition attempt was made. But ultimately, that fell through because of antitrust, largely antitrust reasons. And so then, Halliburton was sort of left with, this difficult situation that its own drilling business is sort of in an uncompetitive state. Actually, at that point, we're a distant number 3 in U.S. land, which is where all the drilling action, it was and is. And so something, the product portfolio was sort of old. It wasn't bad from a performance perspective, but it was old, and it was the cost basis made it sort of uncompetitive, meaning that we couldn't make money in U.S. land. And so we were not in U.S. land as a result. So something dramatic had to be done. So in 2014, 15, when the whole thing went, didn't happen, then, the company, Halliburton Company, made a, sort of conscious effort to invest disproportionately heavily into product development at Sperry Drilling, right? So there was sort of imperative, because we didn't have any business anymore, and without drilling, right, you're not really a full services company. So that was the sort of business imperative that that something urgently needed to be done to refresh dramatically the product portfolio, and and had to be done quickly. That was so. Historically, product lifecycle, because drilling is the most complex, arguably the most complex business amongst all the various businesses in oil and gas, and at least on the upstream side. And so that was sort of the situation in 2015 or so. So I used to be on this M&A team, actually. So I got to see the Baker side, the Halliburton side, all the sides, and so on. So even when this deal was coming apart, we were already sort of working towards what we needed to do to these sorts of things. But
when that happened, how specific was the mandate from management about what they wanted? Did they say they wanted something that looked like this?
No.
Or it was they just said make something better?
Yeah, it's a look, so we knew what needed to be done at a high level, meaning we needed a drilling system which has specifications of performance. It sort of has to be number one in the industry, right? I mean, you can measure, we'll get into it maybe, but for example, things like performance metrics like RPM. So if you have to drill fast, it must spin fast. So it had to have the highest RPM in the industry amongst all the other drilling systems. Then it needs to carry the highest torque, because as you can imagine, drilling is all about RPM and torque. If you can torque it harder, you'll cut faster and you go faster. So highest torque, highest RPM, and highest weight, because you need all three in order to drill fast. So it's quite simple. Then on top of it, it had to have the ability to cover, especially with horizontal drilling. People, what happens is, if you have to drill horizontal wells, you have to start on the surface. So you have to drill a vertical well for sure. Then when you drill the vertical well, then you make a curve, and then you go along horizontal. So this is what the well trajectory looks like. There are two ways to do it, at least. One is to drill a vertical, actually three, pure vertical. Then you do a curve. So you pull out, and you drill just the vertical with one assembly. You pull out, and you go with a special assembly to drill the curve. Then you pull out, and then you go with a third assembly to drill the 5-mile long lateral. Expensive, 3 trips. People want one run, because it saves 2 trips and lowers overall costs, drilling costs.
And to your knowledge, there was nothing like that existed in the industry.
There was. We were like number 3.
Oh, I see. No. The one, there's no technology that could do it all in one.
Nobody quite could do it yet, although Baker had, in some cases, were able to do it. Schlumberger in some basins, but not all. That's sort of the holy grail, is to do it all. So so some could do partly, and instead of 3, maybe they could do it in 2, or some could sort of 1.5 or something like that. So we knew what needed to be done from a specs perspective, but beyond that, they said, money is no option. Pick the best team from wherever, whatever, and go for it. So that was sort of the
Okay.
Yeah.
Okay, great. And then tell us how a little bit. And we've talked a little bit about this in the case, but how you assembled, sort of the organization of Halliburton, how you assembled the team. Yeah. You kind of cordoned them off from the rest of the company a little bit.
Yeah.
Working on a secret project. Maybe could you tell us a little bit about
that? It wasn't secret, but certainly we got the best people from all over the company, and then people think that oil and gas necessarily requires people with degrees in petroleum or geosciences and things like that. For sure it does. But for example, to build a drilling system or some measurement systems and things like this, you actually need all of the above. You need traditional mechanical engineering, electrical engineering, so, control systems, and specialists in a lot of fields. So we hired a lot of new people who had no idea of oil and gas. Who didn't know which end, if this is the drill bit, and which is top, which is bottom, and things like. But they knew all about whatever the specialty was. So it was about assembling the right team with the right skills to pull this off, and then in addition to find the right supply base. Because of sort of the compressed development times, we did not have the luxury of doing everything ourselves. So we had lots of the right partners and suppliers to help us with this.
Okay. Okay. So you had to recruit new people, really.
Yep.
New people. And that was there was a little culture mismatch with the rest of the company, or not?
I mean, I think that's part of the
Yeah.
cordoning them off,
Yeah.
because we insulated them from a lot of things.
Yeah.
So it wasn't, because of the sort of the importance of it, it was actually not too difficult to do.
Okay.
I mean, it was like nobody interfered with this team too much.
Okay. So tell us about the design process. You said, I think you did it in 3 months. Is it a record?
Yes.
Record-breaking design time.
So, I mean, I think, generally in any product development or of an engineered system like these, there is a concept phase early on, right? I mean, in which you evaluate multiple concepts, and then at least down select to a few, and then you begin in earnest sort of a detailed design of those concepts, and then carry them forward until you choose the final concept. And then, here the crucial thing was to choose a platform, a module, in order to control costs, as well as sort of meet performance. The key was to take a platform approach. So much like you might see in the automotive industry, cars share the same chassis or the same engines in order to create new models, which is sort of platforming. This is built on a platform. So it was crucial to get the right platform concept. Because you build these things, you have to build all sizes. There are like 4 sizes of these tools you have to build. And the trick was to choose modularity or the platform concept such that they share parts. So 60% of parts, are shared across all sizes. So, because you have like small size slim tools to big diameter tools, but they share all the electronics and the turbines and, all of those sorts of things are shared, which dramatically reduces capital costs, and also allows you to reduce maintenance costs, operating expenses. So total cost of ownership reduction was sort of a key internal requirement, in addition to performance requirements.
Now, the radial and axial modularity that you told me about earlier, was that something that that there was agreement on from the outset, that we want a drill bit that has these features, or did you have to discover that's what you wanted?
No.
Well into the
because the older generation that we had suffered from extreme lack of modularity, and which is sort of the reason for high cost. And so the team sort of had this in mind right from the start, that we needed modularity. We didn't know exactly what it meant or how we would execute that, but it was absolutely needed. And so radial modularity is what I said, because these things are nothing but cylinders, right? I mean, it looks like a cylinder. And so how do you attain radial modularity? You put a cylinder inside a cylinder. So the inside cylinder is small enough such that it can be used in all sizes. So the only thing you have to change is the outer cylinder to get to bigger sizes. So that's sort of the essence of radial modularity. And the axial modularity is, so this was the sort of unique compared to competition, both radial as well, but certainly the axial modularity is unique in that the the behavior, the steering behavior of these things is largely dependent on how the stiffness variation of this cylinder changes over length, and so by breaking it up in the right way and having sort of super flexible elements in between, you can tailor the steering characteristics of this on a very custom basis. So we when we have to drill for some customers, we look at what needs to be done and tailor the configuration on the fly. So as part of the design. For some other, if you want to just drill a long, big horizontal well, like super fast, then you do it in another way. If you want to drill the full thing, you do it a third way. So that's the notion of axial modularity, the ability to customize these things built off of the same platform. So it reduces capital costs, So the earlier versions, in order to pull these things off, you'd have to create 3 copies of it. And so this dramatically reduces capital costs by sharing of parts. So much like the automotive concept.
Yeah. What was the biggest barrier or obstacle you faced in the development of let's say start with the design phase.
Yeah.
Did you know that you were going to be able to source the parts at the right prices? Was that ever an issue, or there was enough?
The economics of these things is actually the operating cost dominates the capex or the capital cost, just because the life of these tools is 6 to 10 years, and so if you use your if asset utilization is high, then the repair and maintenance costs ends up dominating capex. So part cost directly wasn't a huge issue. What was more important was to find the right suppliers, because we had a compressed development time. We had to, we couldn't experiment with trying to do a lot of these things ourselves. So we just found the right suppliers, and we reused a lot of things from our past products. And this was a sort of largely an exercise in system integration. So it was to get the right system architecture, which is what is unique, different about it, and then secondly, find the right components or subsystems. And so we have a lot of suppliers that we use here to. So we don't do everything ourselves. Yeah.
Okay, now what about the production? So after the design, the 3-month design was finished.
So it's like, the concept was designed in 3 months.
Yeah.
Then, because there are a lot, it takes 6 months for, the lead times for a lot of these parts, for the electronics and the turbines and the generators. Because this has turbines, generators, motors, electronics of all kinds, power electronics, low power, lots of sensors, and lots of computation. So one of the things I should mention is that as a platform, we've designed it that it will live for at least another 10, 15 years, because we don't have, it's too expensive to invest every 3-4 years in these sorts of things. So it's scalable, it's hopefully future-proof for the next 10 years. That's number one. Number two, it's enabled for automation, meaning that ultimately it has all of the computational horsepower and sensors that we need to do autonomous drilling, totally autonomous drilling in the future. And so, in today's language, that talk about edge and edge devices. So this, arguably by that definition, is an edge device. And so it has it has parallel processors, huge amounts of memory. No other tool, just because we're doing it today as opposed to 10 years ago, where all our competition has done their development. We have modern electronics, huge amounts of computational power, downhole memory. So we've just barely scratched what is possible with, So was designed, the architecture, we spent a lot of time on the architecture to make sure it's future-proof for these sorts of things.
So this desire for automation, did that come again from the management or more from the engineers and the?
I think that, first and foremost was a need for something.
Yeah.
So I think a lot of it was because everybody knew, at least the design team, that if we don't do it now, they would never do it. So it wasn't a super, you think that product development is this perfectly orchestrated and super planned process and so on. This was largely quite a bit chaotic, and this ran like a small startup company would. Since I worked in one, I know how it is, and so we ran it like that, and certain things got in, and which if we were more sort of rigorous, or if we did it the more controlled way, may not have gotten in, for example. But.
So in that chaos, was there any grand debate between two, like you were walking down one path and then something happened and you had to pivot fast, or was it more of a bunch of small changes along the way?
Yeah, I think the architecture was the most crucial element. And there were a lot of debates about do I need this sensor or that sensor? But I mean, those are little details, and so we spent a lot of time on the architecture, because if you get that wrong, then you have a fatal error, and then you're like back to square one. So lots of debates at every step of the way. But the other thing that we did, which is unique, is the team. You would think that the team who did this would know a lot about drilling. But by design, we chose a lot of people who didn't know anything about drilling. And yes, there were the few people who we had who needed to know about drilling, but these people were open-minded and not sort of set in their ways on how this should be done or that should be done. So part of the success, I think, is related to having the right people and not the wrong people.
Did you also develop the software for the automation? Is that still to be determined?
No, we're doing that. So I think that we expect, so the firmware, the software which runs this thing, will be developed for the next 10 years, right? Because the hardware is ready and it's super capable in what one can do with it. We expect that the firmware will continue on and be released. We've already released, since 6 months ago when this came out, we are in like version 300. So that is being done concurrently, and more and more features are added and bugs removed, and those kinds of things are all done by the as part of the team development. So we guard that because this is the sort of the essence of what runs this.
And right now, all technology, all navigation is still done. I mean, aside from this, still done manually with humans, right? Mostly.
The steering decisions, I mean, historically, in drilling, are largely done by humans. People, they're called, directional drillers. The way it works is there's GPS, instruments in there which locate where you are. And then these guys will look at we stop, they take a survey, a GPS reading, and then they say, okay, based on this and based on the history of GPS readings, they decide what my next steering action. Should I go up? How much? Should I go left? How much? And then you drill and you take the next survey and so on and so forth. So it's a very discrete sort of thing. You take measurements every 90 feet and on it goes. So because you're taking continuous surveys, meaning continuous GPS measurements inside this, and then you have huge amounts of computation, for sure you can do what the human being can do. You can do it much faster and more consistently. And so that's sort of the essence of what the automated steering is. And so we are working on a autonomous architecture which has sort of multiple control loops. The innermost loop is something which says, I want to go up or at this angle by this much. And so, it's a high bandwidth loop which is running inside and controlling the steering surfaces in order to make it so. Then there is a middle loop which says that, I have a trajectory that I have to drill. And the middle control loop, their job is to make sure that you stay true to that trajectory, even though the formation may be pushing you this way. So disturbance rejection and trajectory tracking is sort of the middle loop. Then there is yet an outer loop what's called geosteering, where, on the fly, someone will decide, this formation based on sensor readings and so on is looking different. The fault is this way, or, I have to go up a little bit. So on the fly, the trajectory changes. And so that's the outermost loop. So each loop runs slower than the other. And so that's the sort of the concept behind autonomous steering.
Okay, so now that once the system was built, when did you start deploying it, and how has that been going?
I mean, we ran sort of the first prototype. This is 2019. So first prototype was, was in March of 2018. When the first things you do in these sorts of things is drill in a cement block, cement blocks sort of half the size of this room, and we have like 10 of them stacked up, and you drill through it to see whether it will behave the way you want it to. So that was March 2018. And then in August 2018, we drilled for the first time at our test well, which is near Waco. And then in November 2018, we did our first commercial jobs. And then, so today we have about 100 runs so far and counting. Maybe it's over 100 now. And so, commercial runs.
Yeah.
And so, so the philosophy here was to fail fast. Yeah. So, historically, the idea is generally you don't make huge bets like this, because in order to run 100 runs, you have to invest huge capital and hope that there is no fatal flaw in this, in which case you'd scrap millions of dollars of capital. So, but jointly, the business and us, we all felt that it's worth taking this risk. And so we invested hundreds of millions of dollars in capital to build, hundreds of these tools and just run them and see what happens. And so that's the process that we are in. And so, yes, we're failing in some cases, but none of the failures is a fatal flaw, And so far so good.
And you've been able to do that one
Oh, yes.
run.
Yeah. And we routinely do it, not just this, we do it totally autonomously.
Wow.
Yeah. But we do this in our test run because customers are generally, it's a cultural adoption thing.
Yeah.
I mean, even our guys who do this sort of stuff, they cannot believe that some machine can do better than them.
Right.
That's number one.
Yeah.
And it's amazing how you sort of see, the reaction is sort of this. Some people do it intentionally. Some people, they find every way possible to make this system look bad.
Right.
Yes.
Right.
So but even and our customers are also risk averse.
Yeah.
Nobody wants to do 5-mile lateral and turn this on, and if it goes the wrong way, then what?
Yeah.
But I think people are changing, and so we drilled recently a well for a customer in the Northeast, and the second half of the well, they allowed it to go autonomous successfully.
That's
So,
great. And your Halliburton management is fully behind the autonomous side of it.
oh, of course,
They
because I mean the benefits of autonomy are, it's not about people losing jobs.
Right.
It's about consistency of operations, and we can show. And I cannot show you the data, but if you look at the quality of the well, of the steering, done autonomously versus human being, it's night and day.
Really?
Oh yes.
Wow.
And the ability to hold a tight trajectory tracking without like overshooting and undershooting and stuff like that. Because if you're drilling at 300, 400, 500 feet an hour, a human being trying to control this is difficult.
What about metrics like the amount of oil you can extract per minute? Is that
That's up to, that's not the metric that is the drilling guys are measured on. As a drilling company, you're simply measured on, here's my well, how fast can you drill it? Can you drill it reliably without any non-productive time? Meaning, I don't want you to go all the way 80% done and then fail. And then I have to pull out and then go back in. You cost me huge amounts of money. So we're not measured as a drilling company on production. We're simply measured on reliability and speed.
And machine is beating man in that sense.
Oh yes, yeah. I think that the always, if you look at the drilling systems, they become more and more complex. They're complex electromechanical systems now, and with complexity comes reliability problems. We have so many electronics and so many wires and connections. And then, drilling operation is remarkably damaging, right? I mean, the shocks and vibrations that you see you just cannot sort of sense it unless you see something like this, huge amounts of shock and vibrations. And you have sensitive electronics which have to be isolated and protected. So it's a technical challenge. So complexity gives you a lot of features, but also increases reliability risk. So it's about engineering, packaging, and isolation and other things so that you can survive these environments. So that's the trade-off.
And my last question would be, is there any, have you done any analysis on environmental consequences of autonomous versus non-autonomous steering? Is there any?
There is no environmental.
There's no difference, right?
If in what sense do you mean environmental?
I don't know. I mean, it's just the.
No. So first of all, here's the trajectory that you're asked to drill. If I drill it even closer to the plan, then there's no problem.
Right.
Yeah. So no.
Okay, great. So do you guys I wanted to open it up the floor to other questions. You guys have, because we have a small group.
I just had a quick question quickly. The technology side of it, do you expect to keep this in-house, and then this is like a feature that you now offer to prospective customers? Like we can do much faster drilling, it's more precise, and it's autonomous if you allow it. Is that something you plan to use as like a marketing feature to potential customers, or would you see it also as a technology to market to other companies and try and sell it or license it out as a potential way to make money on top of it and just increase the returns on the investment?
No, mostly the former. And even there, it depends on how you would monetize. So your question is about how would you monetize the autonomous technologies. And so, it would be for our services. And I think that, always be linked. So we wouldn't sell it to anybody else for sure. But even there, it's not obvious that you would get paid for it. Even if you use it for our services, it depends on how the contract with the customer is structured. So if there are, performance bonuses, for example, linked to speed and reliability, then clearly we would use it and take that bonus, assuming we met the performance. And with some other customers, we would offer it as a sort of an extra item on the ticket, as they call it. Here's my sort of price list. If you want my base service, here's it is. If you want to add automation, here's another, and here's the additional charge, and so on. So I think all of those things are sort of being used.
I have two. First is for iCruise project. The deadline for the project was set at 18 months. And how did you decide the deadline, not 1 year or 2 years? And second one is
What was the first question? It was 18 months.
yes.
How did you decide on 18 months?
I mean, I think generally you have a sense of how long it takes to procure part. Surprisingly, in these, or not surprisingly, maybe surprisingly to you, but that a lot of these parts which go in the system take like 6 to 8 months cycle times. So that largely sets the so it's like design and make drawings, procure, build, and test. So when you sort of add it all up, it's roughly 18 months if you're super aggressive.
And the second one is so this case is Haliburton encouraged the member of the project to fail quickly and frequently.
Yes.
But on the other side, a company should balance the failure cost and the budget.
Yes.
So how did you allocate budget to the?
I mean, there was no like well thought out. I mean, like I mentioned at the beginning, there was this huge imperative, right? Because we need to get this done, and so that skewed this balance, the risk taking a little bit. So we were more allowed to take a higher level of risk than we normally would about this. This is why we invested hugely in capital, taking this risk that there is no fatal error.
So I would assume that Haliburton is working on some other innovations aside this one which was just launched. And so, in your opinion, what was the greatest learning point for you that you can use from this project and apply to other innovations?
I'm going to actually repeat the question so we get it on the mic. So,
Yes, yes.
So what was the greatest learning point from this project that we can use for other?
Yeah, I mean, I think in this first point, many points maybe, but the first one is the urgency or imperative always helps, right? So when there is this sort of crisis, sometimes crises help in sharpening focus, and that condition was there for this. So crises, when used right, can help. Maybe you artificially create a crisis sometimes. Second thing is, I'm speaking from a product development perspective. You have to choose the right people. And so I've always found that, the people who lead, in fact, the guy who is leading this project, he's a PhD also. And so you have to have, technically strong people, but who are also able to lead teams, who are able to influence people, and so all the other things that normally one thinks PhD people don't have. But it's crucial to find, that right person. Sometimes you think, I'll, make the project leader somebody who is, has all these leadership skills, whatever they mean, but they know nothing about the technology. So just sort of case in point, sort of the prior iteration, we had hired a lot of people from NASA. Somebody said, oh, yes, NASA. We should have like great people from NASA because, spaceships and rockets and stuff. But it failed miserably because they didn't have the context. They did not know or didn't bother to learn. Maybe we had the wrong people from NASA, I don't know. But so selection of people is sort of the second learning. key point is to have the right people. The leadership should be technical, yet be leaders, people leaders and so on. The third thing I would say is give them a lot of freedom. Usually in established big companies, you bog down people with huge amounts of learning the sense to see where things can go wrong, and and before it happens, having other things in parallel going on to fix it. So we still have lots of things that are going on right now. By no means is it done. But when we made the choices early on, we set in motion a lot of plan B, C, D, E, F, G, H, I, J in many places. And so, orchestrating all of these sorts of things. But yet when you meet with this Wei, who's the project lead, and you ask him, is it written down? He'll say no. I think, in that sense, it's a very different project because our normal process says everything should be structured, should be written down, you should have a plan, you should have to do this, do that. But yet it wasn't done here, by design.
How much of your electronics do you carry from the previous products? I know you
Yes.
you got it from other people.
Yeah.
Just the electronics, data visualization, data acquisition, and all that. So did you carry from the previous tools, or is it? Because that's always a tricky part.
Yeah.
Getting things from somewhere.
Yeah. No, all the electronics are brand new.
How much of the previous electronics came from? How much of the electronics came from previous products?
Yeah. So we have to be careful. All the when we say electronics, all the electronic boards are brand new. But some of the components on the board are reused. So like memory chips, processors, DSPs, switches, things like this. We may have reused them, because those things, if they're working well, why not? But everything was repackaged and redesigned. But the architecture, the power bus and the communications bus inside this is brand new, and
Have you been able to take any of the technology that you developed for the drill and use it for other drills or other technology within the company? Like, have
Oh,
you
yes.
seen how much of like what you developed
Yeah.
is now in like other products?
yeah. In fact, a lot of things already are being copy-pasted or scaled and copy-pasted over to other products. So, we're doing a new measurement platform. So this is the drilling platform. Usually the way these things work is you have the drilling system. The bit is just a piece of it, but it's the drill system, and behind or above the drilling system is the measurement system, which measures the properties of the formation and stuff like that. So a lot of those things just are benefiting from what was done over here, and then some of this stuff will in time be used in other product lines and so on. So. Mm-hmm.
So when it comes to axial modularity that you're talking
Yep.
about, can the automation deal with changing from, let's say, vertical drilling to horizontal drilling
Yep.
on the fly? Or is it
Yes, I mean the thing is,
Can the drill change from
Oh, yes.
vertical to horizontal drilling
Yeah.
on the fly?
yeah, there are two ways when you can think about it. I think I know what you're maybe alluding to. So one is that the physical configuration is fixed. So today, because we use these very flexible elements along the axis, which are specially included in order to do high curvature drilling, then you have to then manage that flexible system when you do a straight horizontal. Because when you have a highly flexible element and you're going super fast in a straight line, you're more prone to formation pushing you around and going. So it becomes a harder control problem. What would be ideal would be to have a flex which changes on demand. Just like a fighter aircraft, fixed wing to swing wings and so on. So the idea that we've patented this so I can reveal it, but a flex which changes stiffness on demand. So if I'm going through a high degree, I have to drill a curve, I become super flex. And when I go horizontal, I become stiff. So, I mean, we're looking at, sort of, systems which will change its behavior on the fly, which is, I think, what you were asking.
You touched on this topic a little bit, but I wanted to dive a little bit further. Yesterday in Dr. Ray's class, we actually covered a case where a company had a new innovation and it was developed somewhat similarly with this group of people. It was a little more secret there, but once they came up with the technology, they had trouble getting it accepted by other parts of the company.
Yes.
Did you have any challenges with that? And if so, what did you have to do?
No, I think this is a great question because I think that, amazingly enough, when we came out with this, and this has to do with history, maybe, I don't know, it's interesting, but I was shocked that the people in the drilling business, this product was designed to save the drilling business, but yet the people in the drilling business was the most averse to, the reaction was, I don't think it's going to work, this looks ridiculous. And, when the first thing failed, I told you so. I mean, it's like, it's crazy. It's odd when if I still don't understand why, because if had this failed, they would be without a job.
Right.
But yet, these are the people who are still saying, I don't think it's going to work. And it's like remarkable. I don't know. It's maybe a separate study in psychology is needed, but I think now we're getting over these things. But success proves people wrong. Results are sort of facts speak for themselves ultimately. So.
I want to take one more question.
Yeah.
I read a new reference 2018 Harvard, and it says that Harvard was 39th place in the U.S. patent granted in 2018, and also the patent efficiency is industry leading level. So what differentiates Harvard from the peers in the technology and innovation?
So Halliburton is highly ranked in patents and in innovation. So what differentiates Halliburton from its peers?
Well, this is a tricky question because we use patents as a proxy somehow for innovation. It may be true, it may not be true. I think sheer number of patents is one proxy, but my personal view is that it doesn't necessarily imply that having the largest number of patents makes you the best or most innovative. I think it's the quality of the portfolio, meaning, what patents, what are the claims in the patents, what are you protecting, things like this. So, but, sort of people generally use patents as a proxy. So, so we've made a conscious effort to be number one in patents. So, but it comes at a cost. Patenting is not free, and so we actively manage the patent costs and the quality and so on and so forth. But to me, patent is just but one measure of the ability of a company to innovate.
Okay, well, thank you.
All right, thank you.
Sri. Thank you very much for coming here. We really appreciate your time. We have some gifts for you.
Oh, geez.
Yeah, just.
Okay.
Thank you for taking the time.
Oh, thank you. Yep.
Yeah, and well, this is very exciting. Really, really interesting stuff.
Oh, thank you.
So
Yeah.
thank you for sharing with us.
You're welcome.
Okay. Great.
Very good.